Welcome back to the Psyche and Singularity video series. This is the second installment. In the first one, I gave a general overview of the whole book. And in this video, I'm going to go over Chapter 1, the history of the concept of a gravitational singularity. So I am not a physicist. And as a matter of fact, I was talking about this topic a couple of nights ago at a birthday party at a friend of mine's house who was also named Desmond. That's his first name. It's my last name. And in the progress of that conversation, someone said, you can't really talk about physics if you can't do the math, if you're not a physicist. And then my rebuttal was, if you can't understand physics without knowing the math, then why do professional physicists write books for the educated non-expert? They must be assuming that you can understand some of the basic principles, or they wouldn't be writing all these books, putting out all these television series. So I do think you can understand at least the basic framework and some of the philosophical implications of physics from Newton through special relativity, general relativity, quantum mechanics, and string theory, which I will be discussing in this video. And upon knowledge of those basic languages of physics that I'm building my equation of the psyche with the gravitational singularity. So in the original video, I did the overview of the whole book, and I begin the book by talking about how the whole academic enterprise was founded by the philosopher Plato in 387 BCE, just north of the wall surrounding Athens, in a park called Academia. And in that establishment of learning, he picked up on Pythagoras's plan to discover the mathematical forms that describe the movement of the planets and the stars. In Plato's dialogue, The Republic, he has his mentor Socrates establish an ideal society, and one of the main parts of that ideal society is the curriculum of higher education for the ruling elite, culminating with someone he called the philosopher king. And this part of the education, the central part of the education, was a mathematical study of the dimensions of nature, beginning with dimensionless numbers, and then addition and subtraction, which would be like linear, the first dimension, then plane geometry, the second dimension, then cubic geometry, which studies the third dimension, that was not well known in Plato's day, and he said this needs to be developed. And then finally, a study of astronomy and music, which study the fourth dimension of time, or the periodic movement of three-dimensional solids. He said if you study the mathematical forms that describe these four ascending dimensions of nature, you'll prepare yourself to open what he called the eye of the soul to the idea of the good, which is the source of all of the eternal forms, including the mathematical forms, and all of their reflections in the material world in the temporary three-dimensional forms. That when you understand this idea of the good, you'll understand all there is to be known. In the book, I spend some time correlating Plato's idea of the good with Carl Jung's archetype of the self, the ultimate archetype from which all other archetypes emerge, or to which they're all rooted, and also to Plato's idea of the good. Plato's idea of the good is very similar to the gravitational singularity at the Big Bang, the source of everything, this blindingly bright yet empirically unobservable source of all being, including each of our individual selves or psyches. So another point that I repeatedly point to in the book is how ironic it is that Leonard Susskind, who presents his book in an atheistic light as if it is the final evidence against the need for an intelligent designer or a god to organize the universe. He is following in the academic tradition that Plato started, and against his own will, he has, in my opinion, at least nearly completed the curriculum for the philosopher king that Plato had Socrates describe in the Republic, which is the absolute antithesis of the cosmology that Leonard Susskind subscribes to, which is that we live in a universe that just emerged randomly, and consciousness is an unintended byproduct of material forces. Yet his mathematical description leading to his holographic theory of the universe, how the entire three-dimensional universe is a projection from the two-dimensional sphere encompassing the universe, that insight, I'm saying, returns us back to Plato, as Plato predicted that it would. So I will be going over all of these points again and again throughout these videos, but in this video I want to focus on the history of the gravitational singularity, beginning with the movement away from Isaac Newton's theory. So Isaac Newton's theory of physics is that the world is a three-dimensional arena, three unmovable dimensions of emptiness, up, down, left, right, backward, and forward, that those are rigid, fixed dimensions of empty space, and that matter consists of tiny little atoms that float around in space through time, which flows forward everywhere at the same rate, regardless of each individual's relative velocity through space. So that space and time are fixed and absolute. That was Newton's theory, around which he based his theory of gravity. And it works very well for predicting things in almost every situation that we encounter on Earth. However, it does not work once you get down to a small enough level, especially not down to the level of the atom, nor does it work when you are engaging the universe at the largest scales, like a galaxy, or when things are moving very fast, like light, or when things are very heavy. Then Newton's theory does not predict what will happen very well, and it becomes completely worthless at the two extremes of largeness and smallness, and speed and weight. So the first inkling that Newton might not have all the answers came with the discovery of the speed of light, which was the beginning of the downfall of Newton's concept of space and time. So on page 17 of the book, the beginning of chapter 1, I point out, and a lot of physicists who write books about this topic point this out, that in the late 18th century, two other physicists came up with the idea of a black hole. John Michell, an English cleric, John Michell, and the more famous Frenchman, Pierre-Simon de Laplace. They both have said, well, if, according to Newton's equations, if you had a star that was sufficiently massive, its gravity would be so intense that not even light could escape from its gravitational pull, and so they would be entirely dark stars. So the idea of a black hole was even there implied in Newton, and you'll see a lot of similarities between Newton's idea of the cosmos and Einstein's, as we're about to enter into that adventure. And we'll also see Laplace, how he pointed out some of the implications of Newton's theory. Some of those same implications still hold in Einstein's theory. So that's just a prelude to the idea of a black hole. Then in 1862, another French physicist, Léon Foucault, measured the speed of light, which to me is an amazing achievement. 1862, he used an experiment involving light reflecting off of one mirror, then reflecting off another mirror that was rapidly rotating. I don't remember the details of his experiment, but he came up with almost his measurement of the speed of light was almost exactly what we have today, which is impressive. Then, in the mid-1860s, the Scotsman James Clerk Maxwell discovered that light and electricity really are one force, the electromagnetic force. Gravity was a force that Newton had developed the mathematics that described gravity, and then Maxwell discovered that the electromagnetic force, and he was referencing Foucault's measurement of the speed of light, and using that number, he pointed out that the electromagnetic force travels at the speed of light. Therefore, it probably is light. So the electromagnetic force is light, and it travels at a particular speed. But as Brian Greene, the famous physicist from Columbia University, points out in his book, The Fabric of the Cosmos, in none of the four equations that Maxwell used to describe the speed of light did he give a reference frame in relation to which he's describing that speed. The metaphor that Brian Greene uses is, it's like telling somebody that there's a party 22 miles north without saying north of what. It's always 22 miles north. Anywhere you go looking for that party, wherever you happen to find yourself, it's always going to be exactly 22 miles north of that point. It implies that the party is an absolute universal constant, and it's always 22 miles due north of everyone, no matter where you are, which is a strange concept. Then the next step on this historical journey is 1887. Two Americans, Albert Michelson and Edward Morley, measured the speed of light while they were accelerating the source of light and the source of the detector in opposite directions. What they were trying to detect is the underlying, what was known as the ether, the medium through which light was propagating and in relation to which you could measure its speed. But according to their experiment, they discovered no matter how fast or slow they were moving the relative sources of light or the detectors, it always came out at exactly 670 miles per hour, regardless of their motion or that of the light's source. So that, like Maxwell's equations, it implies that the speed of light is absolute. 670 miles per hour, or about 186,000 miles per second. That's the speed of light. But you will always perceive a beam of light traveling at that distance. If you're in a car and you have a flashlight next to you shining light and you're stationary, you had a radar gun that could bounce off a photon and tell you how fast it was going, it would be moving at 186,000 miles a second. So you would assume that if you could speed your car up to maybe half the speed of light, and then you used your radar gun at that light beam next to you, it would be going half the speed of light. But as Einstein will point out, that's not the case. It would still appear to you to be going at exactly 186,000 miles a second. That no matter how fast you're moving or slow, you could be going backwards at near the speed of light and measure the speed of light of a light beam that's being projected from a stationary point, and it would still, according to your measurements, be exactly the absolute speed of light. Einstein came up with that, and that's called special relativity theory, because he took Maxwell's equations seriously. He took the Michelson-Morley experiments seriously. He said, therefore, the speed of light must be absolute. And if the equation for speed or velocity is velocity equals the distance traveled divided by the time spent traveling, like 60 miles per hour, but if the speed of light is always the same, then any change that we perceive must be due to distance or space and time. Space and time must somehow bend and twist in just the right relationship in order to maintain the absolute speed of light. And that was the birth of special relativity. And his explanation was that as you travel through space, if you were measuring a light beam using a measuring tape or a series of rulers and a clock, the faster you travel forward through space, the shorter your measuring rods would become in the direction of travel. It's called length contraction. And also the slower your clock would be ticking, that's called time dilation. And it would be just in the right proportion that you're measuring the light beam. You'd think, oh, now I'm going half the speed of light, so I should be measuring that light beam next to me is going half the speed of light. But your ruler's going to be shrinking and your clock is going to be slowing down, so that when you do that measurement, it still comes out that that light beam is moving at the absolute unchanging speed of light. And so I know that's just a very bare bones breakdown of special relativity, but the purpose for my book, Understanding Physics, is that, as I discussed in the first video, Carl Jung and the Nobel laureate in physics, Wolfgang Pauli, who helped discover quantum mechanics, which we're going to be discussing later in this video, they came up with a theory, which was influenced by their understanding of Plato, that the laws of psychology should mirror and be mirrored by the laws of physics, because mind and matter both emerge from the same empirically unobservable transcendental source, which they call the unus mundus, the one world, otherwise known as the archetype of the self, the God archetype, and the one. So we just need to know enough of physics to point out parallels with Carl Jung's psychology of the self, with which Wolfgang Pauli agreed. He agreed with Jung's basic model of what a self is psychologically, and they were both trying to establish these parallels with the laws of microphysics, but the laws of physics in general. And as we'll see, special relativity and general relativity don't fit well with quantum mechanics, which was developed in 1927, but string theory unites the two, specifically Leonard Susskind and Gerard de Hooft's holographic version of string theory. At least mathematically, it synthesizes relativity theory and quantum mechanics in an elegant way, but it has not yet been empirically verified, another point that we'll be talking about. But just to keep in mind, why are we going through the details of this evolution of physics? Because the overall goal is we're looking for parallels between the laws of psychology and the laws of physics that culminate, I'm saying, with the equation Psyche equals singularity. So to understand what a gravitational singularity is, it helps to understand the development of the languages of physics from which that term arose. So that is the birth of special relativity in 1905. And tied to that discovery, Einstein also discovered his equation E equals mc squared. Energy equals mass times the speed of light squared. And that is going to become very important for understanding my equation, Psyche equals singularity, which is based on Carl Jung's equation, Psyche equals highest intensity in the smallest space, as I discussed in the original video. The highest intensity of mass would be infinite. The smallest space is zero volume. That is the definition of a gravitational singularity, a point of infinite density and zero volume. So connected to Einstein's discovery of length contraction and time dilation, space and time bend in just the right proportion that you always measure, no matter how fast you're moving, you always measure a light beam as going the same absolute speed. And then related to that, all right, so related to that is the equation E equals mc squared. I'll read just a little bit here from Leonard Suskind's book. Well, he just describes that the units of mass that can be translated, the units of mass and the units of energy can be translated into each other using that equation, E equals mc squared. Energy and mass are convertible terms. And also related to special relativity is the idea of the relativity of simultaneity. So Einstein explained a thought experiment to describe what he meant. Imagine people at a train platform, and a train is coming into the station. It's not stopping, it's going right on through. And let's assume it's moving a significant portion of the speed of light. As the train's midpoint reaches the midpoint of the platform, observers on the platform suddenly see two lightning beams, lightning strikes on the track directly in front and directly behind the train. And they see the light from those lightning strikes hit their eyes simultaneously, so they assume the lightning hit the front and the back end of the tracks upon which the train is resting at the same time. But people on the train see the lightning hit the front of the train first, and then they see the lightning from the back. The light has to catch up to them as they're speeding towards the lightning strike that hit in the front, and so they see the rear lightning strike after they see the first one. So who's correct? The people on the platform who see the lightning strikes simultaneously, or the people on the train who see the front lightning first and then the back? Einstein said they're both correct from their relative reference frames. And then from that thought experiment, Brian Greene, he describes that indicates the past and the present and the future all coexist. Now that is a hugely important point for philosophy, and especially for my equation of the psyche and the singularity, and for explaining Carl Jung's near-death experience of the cosmic horizon, where he experienced the past, the present, and the future simultaneously. So I'm going to read a little bit here from Brian Greene, explaining the relativity of simultaneity. He says, once we know that your now can be what I consider the past, or your now can be what I consider the future, and your now is every bit as valid as my now, then we learn that the past must be real, the future must be real. They could be your now. With this bold insight, Einstein shattered one of the most basic concepts of how we experience time. The distinction between past, present, and future, he once said, is only an illusion, however persistent. So, most of us, I think, go through the day on the basic assumption that the past is gone. We have memories of the past, but the past itself is irretrievably lost, and the future does not yet exist. But according to Einstein, the past and the future are interwoven with space. So just like in front of me is still there, even though I am here, and behind me in space exists, even though I am here, so too does the future of time exist and the past exist, even though I'm here in the present. So that's the claim in an eternal soul that arises throughout history, and that the soul can have knowledge of the past, the present, and the future, seems a lot less of a stretch when our own modern physics says that, well, maybe you can be aware of it or maybe you can't, but it does exist in space-time, in what's known as a block universe, that you can slice this block of ice or a loaf of bread of space-time, and each slice is a moment in space-time, and that they all coexist. So that is an enormous leap of understanding about the nature of space and time. But Einstein realized if the speed of light is this absolute speed limit, then Einstein's theory of gravity must be wrong, because according to Newton's theory of gravity must be wrong, thought Einstein, because according to Newton's theory, gravity travels infinitely fast. It travels instantaneously between two objects. Brian Greene gives the example of the vaporized sun. According to Newton's theory, each of the planets would be connected to the sun by a kind of gravitational rope, and that's the gravitational force. And if you turned off the gravitational force, then those planets would careen out of their orbits instantaneously, implying that the force of gravity is this instantaneous connection, which is the same as infinitely fast. It propagates infinitely quickly. So Einstein wanted to see the force of gravity obey the absolute speed limit of light, and he came up with a theory that gravity is caused by the curvature of the fabric of space-time. And the analogy that Brian Greene describes is, and that most people have seen, imagine the fabric, the four-dimensional fabric of space-time as a three-dimensional trampoline. So we are reducing this one dimension to help us imagine it, because we can't imagine the curvature of four-dimensional space-time, but we can see the curvature of the two-dimensional surface of a three-dimensional trampoline. If you take a bowling ball and you put it on a trampoline, you'll see the surface of that elastic fabric bends into a kind of a well. And then if you take smaller balls and roll them on the trampoline, you'll see that they start to orbit around the bowling ball, because they're just following the curvature of the surface of the material that they're rolling across. That is how Einstein describes gravity. You can't imagine it with your normal imagination because we imagine things in a three-dimensional space. But if you could imagine the curvature of the surface of four-dimensional space-time, the sun would be creating an enormous indentation in that surface, and the planets are orbiting around that well of the curvature of space-time. So if you suddenly turned off the source of gravity, or the sun just vaporized, that indentation in space-time would bounce back out and send a ripple of gravity, gravitational waves through space. The planets would continue to go to orbit around that indentation until it rippled out towards them. It would take about 8 minutes for Earth to careen out of its orbit, its circular or roughly circular orbit around the sun. If the sun suddenly disappeared, we would still see light for about 8 minutes, and it would take the gravitational wave to hit it about 8 minutes to hit us. So the force of gravity travels at the speed of light, according to Einstein's theory of general relativity. The special theory of relativity is special because it applies only to objects moving at a uniform rate, not accelerating, whereas general relativity applies to accelerating objects, objects that are slowing down or speeding up. And he also sees the link between acceleration and gravity. As a matter of fact, I have here on page 23, Einstein's first insight into how gravity can be made consistent with the speed limit of light came while he was sitting at his humble patent clerk desk in Bern one day in 1907. So he was looking out of his window and he saw workers on the roof. And he realized that if someone was to fall off of a roof and drop an object next to them at the same time, they would both fall down at the same rate, as if the force of gravity had been turned off. The ball would just, if you had a ball and you jump off a roof, it's a windless day, you let go of the ball hovers there right by your head, as if there was no gravity just because you're accelerating downward. So this link between acceleration, which is an everyday occurrence that we all know about, you feel when you hit the accelerator, you get pressed against the back of your seat. When you are in an elevator going up, you feel you're getting pressed down to the floor, like gravity's intensifying. So this was Einstein saw that link, and it helped him solve the riddle of general relativity, which was related to his idea of acceleration through space slows time relative to you. The faster you move through space, the more you are contracting in the motion, in the direction of your motion, and the slower your clocks are going. Another point Einstein showed is that no massive object, light, a photon has no mass, and it travels at this absolute speed. From its perspective, there's no space and there's no time because it's traveling at the speed of light, in which space gets contracted to zero and time completely stops. But from our perspective, we see it moving at the absolute speed limit of light. If you try to take any other object, or at least an object that has mass, and accelerate it through space, it gains kinetic energy as it's moving, which is equivalent to mass. So it becomes more massive, which requires more energy to accelerate it more. The faster you accelerate it, the more it's contracting in the direction of travel, and the more massive it's becoming, the more energy is required to accelerate it any further. So it's a law of diminishing returns. You would need an infinite amount of energy to accelerate a massive object to the speed of light. And Einstein thought, there is no infinite source of energy, so no massive object could possibly go that fast. To his horror, he discovered after the German artillery officer Karl Schwarzschild, while in the trenches fighting in World War I, he came up with the first exact solution to Einstein's field equations for the gravitational field for general relativity. Einstein's original equations were approximate only. I don't know what approximate field equation means or the difference between an exact and an approximate. All I know is Karl Schwarzschild completed Einstein's proof for the theory of general relativity, and Einstein was pleased with his results. It was on a letter Schwarzschild sent to Einstein, dated December 22nd, 1915. Einstein had that published in January. In February 1916, Schwarzschild published another paper in which he described for the first time a black hole. That according to Einstein's general theory of relativity, if you had a star that was sufficiently massive, it would collapse into a point of infinite density and surround itself with a spherical perimeter where space and time stop. Einstein was not pleased with that second paper from Karl Schwarzschild because a point of infinite density is the same as traveling infinitely fast. If gravity and acceleration are equivalent terms, then a point of infinite gravity is equivalent to a point traveling infinitely fast. Just because I'm thinking of it now, I'm going to bring this up. The Catholic mathematician and theologian, 17th century theologian and mathematician Blaise Pascal, one of the founders of modern mathematical theory, he was thinking about his definition of God, and one of the attributes of God is that God is indivisible and omnipresent. Well, how can something be everywhere, seemingly extended throughout all space, and yet be indivisible? You can't divide it up. I mean, at least in your imagination, you could bifurcate something that's extended in space. So Pascal said, okay, I'll tell you what it is. This was in his series of aphorisms, Pensees. I believe it was number 420. And he said, imagine a point traveling everywhere infinitely fast. It would be at each point of space simultaneously, although it would remain an indivisible point by adding infinite speed. That is a lot like the idea of a gravitational singularity, and Einstein rejected that idea to his death. He rejected the idea of black holes and gravitational singularities, and so do a lot of physicists, because of the idea of infinite density and zero volume. That's no longer a material thing. Now you're in the realm outside of the laws of physics, and it's starting to sound a lot like theology, and a lot of physicists reject the whole notion of a singularity, and I will focus on that controversy in another video. But the mathematics indicate singularities exist, and we have very strong empirical evidence to believe black holes exist in the center of every galaxy, a supermassive black hole, and strewn throughout their masses, the volumes of the galaxies are other smaller black holes, and quantum mechanics indicates that underlying every point of three-dimensional space is what's known as the quantum vacuum, where virtual particle-antiparticle pairs are constantly emerging and instantaneously annihilating each other, creating so much energy that there's an infinite amount of energy underlying every point of three-dimensional space. If you condense an infinite amount of energy at every point, that's another word for a singularity. So that the quantum vacuum underlying the entire expanse of three-dimensional space is constructed of miniature black holes. So we'll be getting into all of these concepts, but I'm equating the psyche with the singularity. The singularity is omnicentric. It's always the center of a encompassing sphere, but the singularity is also at each point of space-time. So it's omnipresent. How can something be at one point and at another point simultaneously? We'll get into all those topics, but right now we're just developing the step-by-step history of physics that led to this concept. So we left off with Karl Schwarzschild, who gave the first exact conclusion to Einstein's field equations, and it ended up with the idea of a black hole. So, which Einstein rejected. Then, in 1917, Einstein realized that the universe should be contracting because the gravitational attraction for every massive object, for every other massive object, it should be causing the universe to pull in on itself. But Einstein thought the universe is static. It's neither expanding or contracting. And so he inserted what he called the cosmological constant into his field equations for general relativity. I don't know what number that is and where it goes, but I know that it was symbolized by the Greek letter lambda, which kind of looks like an upside down Y. It always makes me think of Revenge of the Nerds. Lambda, lambda, lambda. So that's the repulsive force of anti-gravity that Einstein inserted into the equations for general relativity to make the universe constant, so that the inward attraction for all matter would be counterbalanced. But then in 1927, a Jesuit priest from Belgium, Georges Lemaitre, presented Einstein with his theory that the entire universe is expanding, which implies in the past it was smaller. And if you go far enough back in the past, it would have been all contracted into a single point, which Lemaitre called a primeval atom, and that the universe exploded from this primeval atom, and that's where we have, and that the universe today is expanding away from that original explosion. So the mathematics that Lemaitre used worked, but Einstein did not like the idea of this primeval atom, this infinitely dense point. And so he told Lemaitre, your mathematics are correct, but your physics is abominable. So it's important to note for history's sake that Lemaitre wasn't the first person to come up with the idea of an expanding space-time. The Russian meteorologist and mathematician Alexander Friedman was the first one to come up with equations for the expansion of space, but it was Lemaitre who independently put the idea of expanding space into an entire cosmology, and that's the Big Bang cosmology that we have today. Einstein initially rejected it. He said, yeah, the math, it works, but a primeval atom of infinite density, that's impossible. So sorry that I'm just not going to accept that. But then 2 years later, in 1929, Edwin Hubble used the 100-inch mirror in the largest telescope of his day, the Mount Wilson Observatory in Pasadena, California, in 1929. Looking through this enormous telescope, he realized that what were then called starry nebula are actually independent galaxies, and that these galaxies are all expanding away from the Earth, and that their expansion rate increases in proportion to their distance, and that the farther out they are, the faster they're expanding away from us, which vindicated Lemaitre's idea that the entire universe is expanding. So Einstein then accepted Lemaitre's theory and called it the most elegant interpretation of his theory that he had heard when he went back to hear Lemaitre give a talk about it at the Mount Wilson Observatory, if I remember correctly. But at any rate, in the end, Einstein embraced Lemaitre's theory, but he continued to reject the idea that the primeval atom would be that monster that Schwarzschild first discovered, the singularity. That is something Einstein never agreed with. And then so in 1929, when Edwin Hubble vindicated Lemaitre's Big Bang theory, Einstein said his insertion of the cosmological constant into his field equations for general relativity in 1917 was the biggest blunder of his life. But then, as we're going to see, in 1998, Saul Perlmutter was the first. He led a team of astronomers who were the first ones to discover that the galaxies, and they're expanding away from us faster and faster the farther away they are. He wanted to discover how much that acceleration rate is slowing down over time. You would assume it would be slowing down, but to his great surprise, it's actually speeding up. It was as if you threw a ball up into the air, and instead of slowing down, stopping, and coming back down, it just kept accelerating faster and faster and faster. Something that was totally unexpected, but it spelled the reincarnation of Einstein's cosmological constant. This anti-gravitational force would account for this acceleration of the expansion rate of the universe. So we will, I mentioned that now, jumping ahead a little bit, because he called that, in 1929, he called that cosmological cosmological constant, the biggest blunder of his life, but now it's that rejected stone has become the cornerstone for modern physics. It's called dark energy now, and it comes from the creation and destruction of these particle-antiparticle pairs in the quantum vacuum. And we are approaching that, but first we want to talk about the next step in the history of physics leading to our understanding of the concept of a gravitational singularity, and that is quantum mechanics. The same year that Lemaitre came up with his Big Bang theory based on general relativity, another group of physicists discovered quantum mechanics, which was another principle of physics that Einstein rejected. However, unlike Lemaitre's theory, Einstein never accepted quantum mechanics. One of the reasons being that it destroys the deterministic cosmology that Einstein had developed. For Einstein, the past, the present, and the future coexist. So everything's determined and everything's fixed. But then Laplace, he was the first to point out that determinism was also inherent in Newton's theory. If you could know the momentum and the position of every particle in the universe at any given moment, then you could extrapolate exactly the position and momentum of every particle into the infinite past and into the infinite future, and to someone who could do that, the past and the future would be present to their eyes. Everything is determined and fixed. Einstein believed you didn't so much need to extrapolate the past and the future and recreate them in your imagination, because they all coexist. The past and the future exist just like in front of you in space and behind you in space. Still, the point is, the universe is determined. Quantum mechanics throws a monkey wrench in that idea, and it comes down to an understanding of what's known as the double slit experiment. So before quantum mechanics, it was thought that light acted like a wave and that matter acted like particles. But light had some of the attributes of particles, and it was discovered that electrons and the constituents of an atom have some of the properties of waves. So the experiment that was conducted was called the double slit experiment, and it was originally to discover, is an electron a particle or a wave? But it applies to photons and every other quantum particle. So they, and I'm sure a lot of people have seen demonstrations of the two-slit experiment, but if you haven't, or as a refresher, the experiment consisted of shooting electrons through one wall with two slits very close to each other, and then a detector screen behind them. So if the electron was a wave, then it would go through both slits simultaneously like a wave would. Then it would ripple out from each of those slits, and as it rippled out from each slit, those two new waves would interfere with each other and create an interference pattern on the detector screen. A series of light and dark bands, the light bands corresponding to where the two waves amplified each other, where two valleys would multiply and create greater intensity, and the dark bands to where a valley and a peak would cancel each other out, leading to just still water. So that would be the pattern you would expect if the electrons were waves. The strange thing is, when they shot the electrons through these two slits, each individual electron was detected as a single particle hit on the detector screen. But after about an hour, those individual particle hits formed the same exact pattern that a wave would have formed had it gone through all at once. And that experiment has been conducted ever since with greater and greater refinements. They can shoot single electrons one at a time through the two slits now, and the same thing happens. Each individual electron is detected by the detector screen as an individual particular hit, like a little bullet. But when you let time elapse, those individual hits take on the pattern as if a wave had gone through all at once. So the implication is this. Then the other part of this experiment was, then if they set up an electron microscope to look and see which of the slits the electron actually goes through, then those individual hits line up only directly behind the two slits, just like bullets would have done. If you had a machine gun and shot at the wall with the two slits, the bullets would only go through those two slits and line up in two bands directly behind the two slits. When you observe which slit the electrons go through, that's the pattern that you detect. They go through as particles, they line up directly behind the two slits like two bands. But when you're not observing which of the two slits the electron goes through, and the implication of that wave-like pattern that gradually appears on the detector screen implies that the electron goes through as a wave and then collapses into a definite point when it hits the detector screen. Well, what kind of wave does that? A wave of water does not act like that. When you observe water, it doesn't transform from a wave to an ice cube. So quantum mechanics was trying to explain this. What kind of wave is that? It was Erwin Schrödinger who came up with the mathematical equation that describes the wave. He originally thought the electron physically smears out like a wave. But then a series of other physicists, including Max Born and Niels Bohr, Werner Heisenberg, and Wolfgang Pauli, they came up with the theory that the waves are actually waves of probability. What probability are they presenting? The probability for where a particle might appear were you to observe it. So a wave of probability, that is not a physical thing. A wave of probability is a mathematical object, and to this day they call it quantum weirdness, and no one really knows how this could possibly be the case. What does observing this wave of probability have to do with the price of eggs? How does it make it collapse into a point? Does this demonstrate some relationship between an observer and that which is observed? And Einstein didn't like the whole thing because it destroys the determinism that he liked, that the past and the present and the future are all fixed, because according to quantum mechanics, you cannot know the position and the momentum of a particle at the same time, because it moves as a wave, but it exists in space as a point. When you observe it, it acts like a particle. When you're not observing it, it acts like a wave. So if you know its position, it acts like a particle. But the more you know about its position, the less you can know about its momentum, or its wave nature. And the more you know about the wave nature, the less you can know about its position. So as Laplace pointed out when he was analyzing Newton's theory, if you could know the position and the velocity of every particle at any given point, you could extrapolate all of their positions in the past and the future. Quantum mechanics says, but you can't simultaneously know the position and the velocity of the fundamental building blocks. And therefore, at best, even a cosmic intelligence would come up with a probable prediction for where each particle would appear. Einstein rejected that. He rejected that rejection of determinism, and he spent a lot of the rest of his life trying to refute the quantum theory. And one of the ways he tried to do that, but before I move on to Einstein's attempts to refute quantum theory, I just want to read a little bit here from Heinz Pagel's book, The Cosmic Code. It was the first book I read introducing me to quantum theory, where he brings up the history of this discovery of what's known as the Copenhagen interpretation of this particle wave paradox. And I specifically want to mention it because he mentions Wolfgang Pauli, who was right there at center stage with the discovery of quantum mechanics. So I'll just read a little bit here from Pagel's book. By February of 1927, Niels Bohr, Werner Heisenberg, and Wolfgang Pauli had exhausted themselves trying to figure out whether the electron is a particle or a wave. They were in Copenhagen at the time. Bohr took a vacation while Pauli stayed in Copenhagen, lashing Heisenberg with constructive criticism. It was then that Heisenberg and Bohr each had independent insights into the wave-particle paradox. Heisenberg had discovered the uncertainty principle, and Bohr had discovered the principle of complementarity. So together those became the Copenhagen interpretation. Complementarity means the more you know about one aspect of a quantum particle, the less you can know about the other. The more you know about its position, the less you can know about its momentum. So they are mutually exclusive but complementary pieces of information about the same object. They complement each other, but they exclude each other. You can only know one or the other with precision. And Pauli, who is considered the greatest mathematician among these quantum physicists, was right there in Copenhagen at the birth of quantum mechanics, and he helped Heisenberg. Evidently, he lashed him with his mathematical criticisms into coming up with the Heisenberg uncertainty principle. So the waves of probability, Heisenberg's matrix mathematics helped us understand that what they are, these waves of probability. So I've discussed that, I think, enough, at least for this introductory video series. So then the next step in quantum mechanics came from Einstein. So Einstein did not like the determinism destroying nature of quantum mechanics. Because so I'll read a little bit here. According to the Copenhagen interpretation, this is page 31, the best even a cosmic intelligence can do is make a probable prediction about the past and future of the universe based on knowledge of waves of probability. As Susskind explains, Einstein pompously declared God does not play dice. Niels Bohr's response was sharp. Einstein, Bohr scolded, don't tell God what to do. So Einstein, in his attempt to save God's deterministic omniscience, and Einstein most likely did not believe in a personal God, but he did believe in some kind of an eternal order to the universe, and quantum mechanics seemed to be turning that into, at best, a knowledge of probabilities. He did not like that. So, in 1935, Einstein and two colleagues, Boris Podolsky and Nathan Rosen, wrote a paper dealing with what became known as the EPR paradox. So Einstein, analyzing the math of quantum mechanics, said, well, it implies here that any two quantum particles that were ever in contact will always remain in immediate contact, no matter how far apart you separate them in space, in such a way, and I'm not exactly sure what quantum spin means, but if you spin an atom or an electron one way, its quantum spin state of its partner particle that it was in contact with originally will spin in the opposite way instantaneously. The point Einstein was trying to point out is that that implies instantaneous communication between these two particles. So just because these two particles were orbiting in the same atom at some point, now, one of the electrons shoots off and it's in another part of the distant galaxy. If you take this electron that's still here and you alter its spin state in one direction, instantaneously the spin state of the other will rotate in the opposite direction. So therefore quantum mechanics must be incorrect because it implies this infinite speed, just like Newton's theory of gravity implied an infinitely fast force of gravity. Quantum mechanics implies an infinitely fast force connecting quantum particles. Therefore, it must be wrong. The irony is that 30 years later, in 1965, John Bell, an Irish physicist working at CERN in Switzerland, conceived of a way to test the EPR paradox, and that test was conducted first in the University of California, Berkeley in 1972, but the most comprehensive completion of that experiment came in 1982 from the University of Paris South by a team led by Alain Aspect. They proved that, yes, there is this instantaneous connection between quantum particles that were once connected with each other. So what are the implications of that? Well, one of the implications that another physicist whose book I read, his last name is Gribben, In Search of Schrödinger's Cat, he says, if everything that ever interacted in the Big Bang maintains its connection with everything it interacted with, then every particle and every star and galaxy that we can see knows about the existence of every other particle. Every particle in the universe is in instantaneous communication with every other particle, as if they were all still superimposed into one point of infinite density and zero volume. That's another obviously important philosophical concept, and the physicist David Bohm who was the first one to try to combine general relativity and quantum mechanics using a holographic paradigm, even though Leonard Susskind never mentions him, a point I discuss in the book. If you're Leonard Susskind very generously gives credit to all of the physicists who have historically played a role leading up to string theory, but he leaves out David Bohm, whom Einstein was very fond of. And I think the reason is because Bohm interpreted this holographic combination of general relativity and quantum mechanics in a pan-psychic way. That, here's a quote from John Gribben, again from In Search of Schrodinger's Cat. He says, theorists such as David Bohm argue that we must accept that literally everything is connected to everything else, and only a holistic approach to the universe is likely to explain phenomena such as human consciousness. So that is the exact opposite of what Leonard Susskind is trying to do. He wants us to see human consciousness as a byproduct, an unintended chemical byproduct that emerged at a specific point along the Darwinian timeline, not as an inherent ingredient of the cosmos, which is how David Bohm saw consciousness based on his holographic interpretation of cosmology. So here's a point. Leonard Susskind, his book, The Cosmic Landscape, in that book, he was trying to destroy what he called the illusion of intelligent design. And so the implication is there's no need for an intelligent God to design and fine-tune the universe to create human consciousness. Those parameters of physics that are so seemingly fine-tuned emerge automatically if there's an infinite number of parallel universes, that even the most remote chance of these constants of nature being perfectly organized in just the right way, especially the cosmological constant that describes the expansion of space-time, they will emerge without the need for any intelligent designer if we've got an infinite cloud of parallel universes. Just the right combinations will arise automatically. But it seems to me that if you believe the past, the present, and the future coexist, which is what relativity theory tells us, then that throws a monkey wrench in the Darwinian theory, the standard version of it anyway, because each point on that Darwinian timeline will coexist. Each point on the past, the present, and the future will coexist on this timeline. So maybe there's no need for an intelligent designer, but neither can you say that consciousness randomly emerged at a specific point on that timeline, because all of these points on the timeline coexist. So I'm seeing now we're already 56 minutes into this video, and I've got through special relativity, general relativity, and now quantum mechanics. I'm going to end this video and we'll pick up the attempt to unite these two theories, general relativity and quantum mechanics, which created all kinds of problems. And we'll pick that up on the next video. So thanks for watching. Please leave comments or questions if you have any, and I will see you in the next video.
Boy.